Thank you. So good afternoon, everyone. We are going to start now with the fifth and final session of FMT 2021. And it is my great pleasure to introduce Professor Laura Kovács from Vienna University of Technology, where she leads the Automated Reasoning Group. She's an expert on formal software analysis and verification. And in particular, she's interested in designing new methods for computer-aided verification. She will talk to us today about automating teaching efforts for deductive verification in the context of online teaching and online assessment during the COVID-19 pandemic. So Laura, you can start when you're ready.
Thank you very much for the nice introduction. So let me just share my screen. I believe you can see it. And so I think it was a very nice Sunday. So actually I decided to participate in each talk except one talk when I had to come to university. So I missed one talk of the workshop, but I really liked it. It's a very different workshop, and I'm quite honored that I'm the one closing this workshop and reflecting on our teaching efforts for deductive verification at the Technical University of Vienna. Many things have been said. So I also in my course, we do OR triples, we do SAT SMT. So I can relate very well with the efforts that Jeremy was presenting or Luca highlighting intensive course blocks. So I will kind of overview a bit of that, but there will be one thing which I'm going to focus, which as Alexandra mentioned, thanks or due to this pandemic, we had to really switch to online teaching and to online examination. And especially when you come up with online exams where students have to do logical proofs or derive correctness of programs, it was quite challenging to make sure that students don't cheat while doing online exams. So I'm kind of reporting on that, what kind of framework we came up with that. But for that, okay, so let me just tell you what we do in my research group. So we developed new methods and tools for automated deductive verification, in particular with static analysis, use symbolic computation and automated reasoning. And our focus is mainly on invariant generation, probabilistic inferences, so analyzing both deterministic and probabilistic programs, and also trying to come up with automated approaches to prove properties in the first theories of various data structures. And since we try to do it automatically, we come up with a bunch of tools depending on the domain. We implement various approaches. For invariant generation, alligator, absinthe, or polar for probabilistic inference, and probably most notably that you already heard in this workshop, the vampire theory improver. So this is our research perspective, and as the previous talk also asked, how many of us actually do both research and teaching in deductive verification? Well, we do. So we also teach master lectures, currently so far only master lectures, related to various aspects of automating deductive verification. And especially we have two such courses in which I'm involved as a lecturer, so I'm the lecturer. One is formal methods in computer science, and the other course is automated deduction. And just to give you a bit of background, what is the setting of these courses? So formal methods in computer science, it's a mandatory master course. It's recommended for the first year of master, but it's one of the courses the students are taking multiple times or really postponing to the end of their master studies. It is offered in both terms, so they can take it both in a winter or in a summer term, and it's organized over 14 weeks, each week with 2 lectures. And we actually have between 350, 450 enrolled students in this mandatory course. And now the other course, which it's an elective course, is automated deduction. It's only offered in the summer term. And since it's elective, so less people are taking, but only the interested ones. And it's very interesting to see this ratio of 10%. So when I was drafting the slides, I realized that while formal methods in computer science is mandatory for all students in logic and computation, software engineering and computer engineering, automated deduction as an elective course is taken by about 35, 45 enrolled students. Mainly logic and computation and engineering, but we also have students taking the course from mathematics. So now what we try actually, since I joined Vienna and over to these 2 courses, is we really try to bring our research into teaching. So we show recent progress in deductive verification or in automated reasoning by pretty much also bringing our progress or our tools into the course and supporting our teaching efforts. And actually we automate some of our teaching efforts in our courses for deductive verification. And this is what I'm going to tell about today. So how can we actually use, for instance, Z3 or Vampire, some automated tools that you already heard about, to also assist us in generating online exams. So let me just tell you the context, a bit more the background for formal methods of computer science. So what do we expect in that course from our students? And it's really similar to what you heard from also from other talks. So this is a mandatory course. It's a big course. So it's meant 6 ECTS, but actually it's a 9 ECTS course. So it's the biggest course our faculty can give. So 6 ECTS for lectures and 3 ECTS for exercises. But I only put now the course here. And what this course is about also as an introduction when we try to motivate students is that, so we kind of go into 4 blocks. So the course is organized in 4 blocks. First, we start with what can be computed and how it can be computed, touching about a bit upon theoretical computer science. And then the 3rd and the 4th block, so the last 2 parts of the course are about how can you ensure correctness of computations and how can you automate that insurance process. So it's we are covering logic and computability as well as verification by going through foundations of complexity theory, introducing decidability or overviewing decidability and undecidability results, making sure what it means to have to work with Turing complete languages. Then we focus on subclass of programs for which we tell, okay, well, this such as satisfiability problems that we can efficiently compute with. And then we focus on 2 approaches in terms of verification, deductive verification, and model checking. And we kind of try to explain them the trade-off or the advantages between the 2 approaches. So my block or my part in this course is mainly on deductive verification, but I've been also teaching model checking. And what we do here, as in the previous courses you heard, or previous talks you heard, it's an intense course. So we have 3 weeks teaching period for this block. So it's between 6 lectures or 5 to 6 lectures. We have to cover operational and axiomatic semantics. Then we introduce HOAR logic to present or describe program correctness in using HOAR triples. Then introduce the weakest precondition approach for doing algorithmic verification, generating verification conditions. And 1 lecture in the course is really about invariant generation. So for some classes of programs, we actually show students that generating invariants can be, it's decidable. And so we don't give students, in the exercise, we don't give students the invariants, we actually ask them to prove program correctness, either partial or total correctness, by coming up with appropriate invariants. And we also practice, so we support deductive verification using Daphne, that was already mentioned in the morning by Rani. So, and this is now where the research that we conduct in my research group comes into the play, because we actually use our research on invariant generation to teach invariant generation, and also to provide students exercises, practice sets, exam problems, and kind of explain them some very simple idea going back to recurrence relation analysis or discrete math that they can use with very simple arithmetic for some classes of programs. They can come up automatically with the necessary invariants. So here's how we start, and now it's coming back. It's a complicated program, and since Fibonacci numbers have been mentioned also by Tobias and later talks, so now I show the imperative version of computing Fibonacci numbers. And this is just a motivating example for the students. We don't really expect them to solve this problem. It's a very hard, it's quite hard for them to come up with invariants among Fibonacci numbers. But in principle, our research on invariant generation, if you give us such a program, we can generate you such an invariant. So an inductive property over the program, and we explain to students what it means, what is the difference between a property being invariant and being an inductive invariant. And we also tell, okay, well, we mainly focus on inductive invariance because these are the properties that we can reason about, or we can automate proofs with. So for this, I actually show students our tool Alligator. They are encouraged to use it and to try it out on some programs to generate invariants. And then using Alligator, they can actually double check whether the invariance that they are generating is very similar or close to the invariance that the tool is generating. So now all good. And now, especially during the past 2 years, because everyone had to move to an online teaching framework. Now we had this problem that we provide exercises to students and they have to solve it, or we give them exam problems and they have to solve it. And we want to make sure that they don't get the same problems. So, or at least they get problems with variations in order to minimize the cheating or the collaboration efforts that they might implement during solving exercises or solving exam problems. And for that, actually, it was a nice time match. We use our approach in which we reverse engineer invariant generation. That is, so we start generating exercise problem from students by using program synthesis from formal methods. So what we do actually, and this is our tool Epson that also implements it, we start with an invariant, a polynomial relation among some program variables, and we ask the tool to generate as a program such that that program has the invariant as the given invariant. So we give a polynomial relation and ask the tool generate as a program that has this polynomial relation as an invariant, as an inductive invariant. And then we take that program and put it back to as an exercise or an exam problem for invariant generation to the student. And then ideally, the student should find the invariant or similar invariant that we gave them. Or at least they should find some invariant with which they can prove correctness of the program with respect to pre and post condition. So now it's, of course, this is, I mean, it's to some extent it's great, but starting with such an invariant, this will be quite hard on our students to come up working with Fibonacci sequences, which actually reduces to work with golden ratios or square root of 5s. So we have to be careful, okay, what kind of invariants are we giving to the students? So what we do, okay, we kind of fix, pretty much we can take an arbitrary polynomial relation among program variables and try to generate a loop with respect to that invariant. So we fix an invariant template and infer a program using absinthe. And for instance, if we just take this polynomial invariant, then we can infer with absinthe this particular loop, one of these loops. And now this loop actually has been used as an exercise and exam problem in formal methods in computer science in our lecture. So we would give students this particular program as an exercise and exam problem and ask them prove the correctness of this program with respect to given pre and post condition. And we make sure that the pre and post condition are such that the invariant is really needed. So for instance, we don't use false as a precondition because then you don't really need much invariant reasoning there. Now, the question is, how do we fix this invariant? So what kind of measures do we implement in fixing the invariant? And we have to be a bit realistic, okay, how much, because it's even if we fix the invariant and our tool generates some loops with respect to that invariant, I mean, the students will have to reverse engineer our process. So we want to be kind of fair and minimize their arithmetic effort or mathematical efforts in large computations. So what we say, we just really do syntactic measures, and it's very flexible. So you can put, or you can generalize with your own syntactic measures. The measures we said, okay, we consider programs with at most 5. We actually consider invariants with at most 5 program variables. It doesn't mean that the program contains only 5 variables. A program can contain more variables, but we consider invariants with at most 5 program variables. We also say that the invariant should be a polynomial equality among program variables, and this polynomial should be of degree at most 3. And this is such because from the theory from loop synthesis, we know that if you have a polynomial of degree at most 3, then you can have at most 2 multiplications among program variables. So the program will be not too complex for the students. And we also say, well, our invariant should be also not too complex in terms of Boolean structure. So we usually work with just conjunctions, so no disjunctive invariants. And we just take invariants as a conjunction of at most 3 polynomial equalities. Usually in our example so far, we only took either one single polynomial equality or a conjunction of 2 polynomial equalities as an invariant. So in this particular case, here we have a polynomial invariant, just only one polynomial equality among two program variables, and the polynomial degree is at most 3. And then we ask Epson, for instance, to generate us a program that would have this invariant as an inductive invariant. And this would be such a program, and then we can feed it back to the students. With this program, actually students can manipulate quite well, since we introduce our invariant generation approach. Now the issue is that from a given program, so for a given invariant, there are multiple programs. It's not just one thing. So there can be 2 different programs satisfying the same invariant. And you might say this is a burden, but it actually was the benefit that we use for generating unique exam problems or exercise problems in our course, because we started with the same invariant, but then we generated multiple programs and use all these multiple programs as different exam problems for the students. But yet again, now the question, from this invariant, for instance, we can use our tool Epson to generate you two different programs. Now the question, which one you use, or which one is more fair towards the students? To some extent, you may say, well, this program on the left-hand side colored in orange is simple because it only uses 2 program variables. But it kind of has a dependency between the variables C and N. So students will have to kind of structure their reasoning for generating invariants. Even more, you have here multiplicative relations. So again, we impose some syntactic measures when we select what kind of programs we keep for exercises for the students. We will go only for affine loops or blocks of affine loops. That is, it's pretty much, so for instance, factorial cannot be expressed in this framework, but you would have only linear updates with some constant multiplications. We only allow restricted, or actually ideally no dependencies among variables, so it's easier for the students to do to infer invariants. We focus to integer valued coefficients, with ideally between, so all these constants that you actually have 1 times c plus 1 times k. Well, you can have also 2 or 3 and so on, but then of course you might have you might end up with from the theory we know you might end up with exponential reasoning. So we try to work with small initial values and small integer valued coefficients. But all these are syntactic restrictions, so you can actually enlarge them or drop them and come up with more complex programs, provided your students will like it. So in principle, with this framework, okay, just by using syntactic measures on the template of the invariants and on the template of the program you want to work with, we can generate quite many individual problems for invariant generation and proving partial correctness of those programs. And that has actually allowed us during the past 2 years or during the past 4 terms to generate unique exam problems. So we have quite many students. So as I said, we have about over 350 students enrolled, and every term at least 140 students are taking the exam. So we need to do all kind of renaming, shuffling, different kind of unique problem generation to make sure that while they're doing the exam, they do not collaborate. And we use actually our approach from reversing invariant generation to come up with unique exam problems for students. So for instance, this would be one such example that we would generate with our tool. So our tool actually will generate the loops, and then we will, on top of it, we will pre-process it and come up with some pre and post conditions. And we will ask them, I mean, this is now an exercise problem, so students can practice quite a lot, but we will actually ask them for each of these 3 loop OR triples, come up, prove or disprove correctness using COA rules, weakest liberal preconditions, and as a practice set in the exercises, they are also required to prove it with Daphne. So now, The invariant, so there is kind of this approach for generating programs from invariants would really come here in this part C, where you have an equational post-condition on program variables. So you need also an invariant that relates program variables, and it's used for proving correctness. And interestingly, so we actually expected that due to Corona and due to the online exam platform, the performance in the course will improve a lot, but it was not. So surprisingly, we had the same success or the same failing rate as before in presence examinations. And interestingly, even the distribution in the grades. So in Austria, we have a grading system of 1 to 5, 1 being the best and 5 being the only failing grade. Even the distribution between the passing grades from 1 to 4 was very similar to in-presence exams. So to some extent, it's very hard to say for what is the real reason that students didn't collaborate, but we are happy that they didn't manage to collaborate better to improve their course performance. And now, after this course, so also during this course, when I finished block 3 on deductive verification of programs, at this point, students kind of know already, okay, what does it mean the program being correct? What does it mean that the program is partially or totally correct? And how you come up with fixed point invariants, so invariants, inductive invariants. But all the proving effort in this course is pretty much done in practice by Daphne or in pen and paper by hand. So as a follow-up course, then students who are interested in the topic can actually take the course in automated deduction. And as I said, this is an elective course. So in principle, only students who are interested in logic and computation would be taking it. And we have about 35 to 45 students rolled up for the course. So let me just tell you about this course, which was even more challenging in terms of effort, because we are covering a wider range of, or we are covering more topics than just deductive verification or just this. Well, deductive verification is also complex, but in the automated deduction, we go on to more in the theory and practice of SAT solving, the theory practice of SMT solving, and first the theory improving. So to some extent, it's quite related to what also Jeremy was presenting, okay, on the logic and modeling course. And we really do the theory and practice. So I don't really have yet a textbook. We are also working on it, but we are not yet organized at Jeremy, so we don't have a Git account for the book. We hopefully come up soon with a textbook. So, but we provide lecture notes and slides to the students. And we really go in terms of, start with basics, SAT solving, present splitting, DPLL, polarity optimizations, Clausian normal form computation, random SAT solving, and then also ask students to test and try out their knowledge using Minisat. So we use Minisat in the course. We also encode Sudoku or logical puzzles, and actually we ask the students to encode. So we do some practice with encoding Sudoku and encoding some logical puzzle, and then give them other puzzles to encode them and ask them to encode them. Then we move to the SMT solving, so showing the general principle, starting with first the theories, first what does it mean to be satisfiable modulo theory, introduce the DPLL theory approach, go towards Nelson-Oppen, and all this supported using Z3 as a practice. And then SAT solving and SMT solving will be one half of this lecture, and the second half of the lecture would be first the theory improving. So it's more a research-oriented lecture because it's really so the first theory improving is really also what we work in as researchers in my research group. So we start with resolution and equality reasoning. So we introduce superposition, and then the saturation, ordering, redundancy are all these practical aspects in order to make first the theory improving efficient in practice. So in principle, after either of the 3 blocks, after the SAT solving block of this lecture, students could in principle implement DPLL-based SAT solving, or they could implement a Nelson-Oppen procedure for SMT solving, and they can also actually encourage them, but they haven't yet really done it yet, implement their own first the theory improver. It's a block course, so 2 lectures, each lecture of 90 minutes, 2 lectures a week, and we teach during 6 weeks. 7 weeks, sorry. Yeah, and actually, I wanted to just thank Jeremy for this asylum example, because I'm also struggling in the lecture to kind of rotate the puzzles or the kind of examples, how to illustrate the challenges of first the reasoning. So I think for the next lecture, I might use your example and show that it can be even more interesting than the one that we are doing. Because what we are doing, we just use examples for motivating first the theory improving, either from the verification aspect was covered from SMT solving. And in our course, we actually use abstract algebra. So the standard problem from abstract algebra, that if you're given a group that satisfies the identity that 2 times the group operation equals a neutral element, then the group should be commutative. So we start with this English natural language problem. And then we go, this is kind of one of the motivating example of our first theory improving, and one lecture just focuses on how we formalize this problem into the input language of a first theory improver, in particular using the so-called TP-TP language syntax that first theory improvers would implement. And we introduce students to that. So for instance, this would be one we explain them, students become also familiar to the TP-TP input, understand the challenges or mistakes that they can make in encoding problems as inputs to first theory improver. And then once they know how to encode, they just run Vampire. So that's a nice thing of an automated prover, and they get this kind of proof. So now this is a small proof. And this is where the first lecture in first theory improving would stop. And students are told, okay, so all these things, all these keywords that you see here, they should understand by the end of the lecture. And if they actually understand it. So by the end of the 7 weeks, they know what it means: superposition, forward demodulation, backward demodulation, clausal normal for transformation, proof by refutation, and so on. So what, and then the exam comes, and the exam already before Corona, it was an open book final exam. So students could take whatever they wanted to the final exam, because the exam problems were really on solving problems using optimized SMT solving, ordered resolution, superposition for organizing proof search. And we also asked some sumness proof for modified inferences. So we changed some inference rules or came up with some new inference rules and asked, okay, is it sound? Is it a rule that we would say simplification rule? But now, again, during Corona, so now it was already open book before Corona. So now during the COVID, we went again to online examination. And we actually had only 2 months to implement, to come up with a reasonable solution, where monitoring students is almost impossible. Although with 35 or 45 students, you might think, okay, you could still monitor. It's impossible to know what they really do in the room while pretending that they solve the exams. And given that we really focus on problems on which they have to come up with logical solutions or algorithmic solutions, a multiple choice exam format was not feasible either. So what we did, actually, we used automated reasoning to create unique exam sheets on automated reasoning. And how we did it, and I will just show you what kind of problems we created, and this time completely automatically. So whereas in the previous lecture in deductive verification, only the invariants have been, or only the programs have been generated automatically, in this process, we generated all exam sheets completely automatically. So let me just tell you how during the what kind of problems students are asked to solve during exercises and also during the exam. Let me just start with telling you that, okay, there are some trade-offs, of course, when you try to come up with an automated generation of exam sheets. You need to be kind of careful that, I mean, the exam should be sufficiently different, but they should be also sufficiently similar. Whatever similarity means, of course. And given that we know that we have at least 35 enrolled students, then we have to generate at least 35 instances of each exam problem. So the generation of this exam sheets has to be fairly efficient. And we also do soundness checking namely that all the problems that we are generating for SAT solving or SMT solving or first order theory improving, we actually prove them also using MiniSAT, actually using Z3 for SAT and SMT and using Vampire for first order theory improving. So we just double check also that indeed the problems we generated are either valid or satisfiable only. And how we do it, we usually take a combination of random generation of problems with some filtering of problems that are good or they're not good or not feasible for the students, and by varying some problem templates. And all this again using just syntactic measures. So you can vary, I will show you what kind of syntactic measures we use. And in principle, you can vary the syntactic measures fairly easily in the framework. So here would be one exam problem on SAT solving. And the problem is formulated such that it's very generic except the core formula. Okay, so we go through, okay, so it's the easiest problem to do because students are asked, okay, answer, okay, which atoms are pure, compute the clause and normal form and decide satisfiability of this particular formula. So the challenge, this is a quite generic question. So we formulate it so that it's quite easy to generate different problems with generic questions. So what we need to do here, we need to generate the respective formula for, so different formulas for different students. So we kind of use again syntactic constraints during arbitrary formula generation. And we do it, we fix a number of variables and connective. So usually we would allow only 5 to 6 propositional variables. We make sure that because of the theory behind of polarity optimization, we make sure that there are at least equivalence, implication, or negation appears at least once in the formula, because otherwise polarity computation makes no sense. Or the naming definition in clause and normal form definition makes no sense either. Then we make sure, for instance, so sometimes because it's a random generation, we could actually come up with some sub-formulas such as P and not P, which can be immediately simplified into false. So these things we will just take away, like immediately simplified. And other measures as well. And then we also do some kind of post filtering. So once you generated all these formulas to be used for the exam, so if you fix your initial set of variables to be 3, then let's say all 3 variables should appear. We make sure that in this problem there is at least one atom of pure polarity. So this is by just traversing the abstract syntax tree of the formula we generated. We vary what kind of clause or normal forms the student should work with. So sometimes it's fine to, so the naming definitions either come with negative or positive polarities. And all these syntactic constraints as post filters could be just applied or checked in the abstract syntax tree of the program, or of the formula. And here we, for instance, would be different examples. So 5 different examples that would be completely generated automatically by our framework. And this means that, so these exam problems would be, this pattern here would be instantiated with either of these 5 examples. So you immediately get 5 different exam problems. Now, let me just go, also depending on the time. So let me go from the easiest to the hardest part of the course, which is really first order, so non-ground quantified reasoning with so-called redundancy elimination, so efficient equality reasoning. And here would be an exam problem. So also this kind of problems we also generate for exercises, and then a similar problem comes for an exam. So we give the student this particular inference and ask, okay, is the inference sound? But actually here we even tell them it is sound, so they have to prove it using logical consequence and using first order reasoning. In this case, is superposition. And then we also ask this question, which is more technical in the first order community: is it simplifying? That is, that simplifying inference rule would mean that you apply this inference and you remove something from the search space. But students know so actually with this question, whether is the inference simplifying, students will have to explain, okay, what does it mean to have a simplifying inference, and then actually show it why it's a simplifying inference. So again, these are quite generic questions. So requires here is that, again, we can just implement some syntactic constraints during arbitrary formula generation for coming up with some this kind of inferences. And for that, again, we fix a signature, but now it's not, we don't only have propositional variable, but we also say you can also have logical variable function symbols and predicate symbols. We generate 3 random literals, but of course you can go higher, but in our setting 3 was enough. We generate random substitutions, arrange the 3 formulas or the 3 literals into an inference rule. We check soundness with a vampire, so we make sure that the inference is indeed sound. So students prove something that we already know that is sound. And then we also make sure that it's a simplifying inference. So by generating a random substitution and arranging it in the respective order of the 3 literals, we make sure that the inference is simplifying, and we check it with vampire. So now let me just go for SMT solving. So this would be again another problem that students would be asked in the course and also in the exam. You're given a particular formula, and is this formula satisfiable? And they're asked, okay, you have to use reasoning in combinations of theories by using Nelson-Oppen and DPL-based reasoning. And now the issue here is that the previous framework doesn't really apply complete. So there has to be something in addition, because it might be that especially for the SMT formulas, maybe also because of time limit, we couldn't come up with a better framework. It might be that you come up with an SMT formula, which might be satisfiable or unsatisfiable in the combination of theories, but you can just deduce satisfiability or unsatisfiability by reasoning only in one theory. And what we want to have here from the students that they really do the Nelson-Oppen procedure. So they exchange information between the theory of arrays, uninterpreted functions, linear arithmetic. So complete arbitrary generation of these formulas might not be sufficient, because we might end up with some formulas that don't require actual reasoning in all theories. So therefore, in this case, what we did, we actually also fixed formula templates, and then you applied syntactic shifts or syntactic changes in these formula templates. For instance, we shifted integer constant by small values, ensuring that the reasoning task really remains essentially the same for all students. And by shift, okay, here's an example that by shift I mean. For instance, one student might have FB doesn't equal B plus 1, and another student would have, okay, in the formula would have a shift by 1. So instead of B, it has B plus 1, and then also not equal to B plus 2. And you can shift it up or down by some small integer constants. And now probably the trickiest one is, although it's only ground, so you might think that actually the first order setting is more complex. It can be actually more complex, but in our setting, we kept it simple. But when it comes to combining equality reasoning with all benefits of all kind of efficient implementation of first order theory improving, that is, you have orderings, you guide the search space, you eliminate things from the search space. And this is what students practice also during the course, and they also understand what does it mean. So the task would be, okay, so you're given this particular 4 formula. As a logician or as a mathematician, you will try to prove it by whatever ways you can have it. Now, as a the theory improver, you are given 4 inference rules, and you have to make sure that the prover is going to find the proof, given that this set of 4 formulas is unsatisfiable. And then in the course, we introduce order superposition, simplification ordering. We tell them how to guide search space, or how to guide the prover to find a proof relatively efficiently. And now for exam problem, we want to kind of replicate this knowledge. We want that students show that they know how that means order superposition. They select the right inference step in the prover, and so on. So we fixed this formula template, but in addition, we also fixed so-called template, also fixed ordering, so syntactic measures on the simplification ordering. And now this is again the theory, but the nice thing about first the theory improver is that in principle, you have first the theory improving modulo a particular ordering. So if you change an ordering, your prover will come up with a different proof, which means that even if you would use this set of problems with a different kind of ordering, the two solutions would be different because the prover will, or the student will have to come up with a different proof based on the ordering. So we kind of vary this kind of measures in generating exam problems. And now, by assembling all these parts from automated generation of problems on SAT solving, SMT solving, ground superposition, and quantified reasoning, we put essentially really put all this together using Haskell. And, I mean, some parts were implemented in Haskell, some were in Python, glued together. All problems have been checked. So SAT SMT solving problems have been checked using Z3. Ground superposition first and theory improving problems have been checked for soundness with Vampire. And then we converted everything to LaTeX. And so it's thanks to Jakob and Petra. We have a joint paper on this also at SICAM, just presenting our experience report. And in a way, this would be an exam problem that we really generate completely automatically from some templates and syntactic measures on how problem 1, 2, 3, and 4 should be. And we, in 2020, when the first instance of the course had to go in completely online setting, then we had to generate 42 such different exam problems. And different in this case means that all the problems 1, 2, 3, 4 are completely different from the other problems, from the other exam problems. So it's not just shuffling about of exam sheets, but it's really every exam problem is different than the other exam problem. So now, to sum up, we didn't envision this, but we actually used automated reasoners to automate some of our, or automated reasoning to automate some of our teaching efforts within online exercises and exams, in particular informal methods of computer science and automated deduction. I mean, we hope, based on the student responses, we believe we did find a balance between variety and fairness. And we already reused the framework for, so since 2020, so in 4 terms at TU Wien. And as I said, interestingly, the exam performance, so although students had open book exams, so they could have, in principle, they could have done whatever they wanted in this 2 or 3 hours exam slot. The performance didn't change when compared to previous in-presence exams. So the number of best grades or the number of passing grades was proportionally pretty much similar as previous in-presence exams. And so to some extent, based on all these efforts that we do now in formal methods of computer science and automated deduction, so we managed to get, so we are reshaping our curriculum at TU Wien. And now we will have logic and reasoning as a mandatory, or for some mandatory and for some elective, a bachelor course starting with the fall next year. And the plan is that we really do a combination of the first 2 courses, but we will not go into, let's say, non-ground superposition, but we really go into the theory and practice of SAT, SMT, and ground theory improving. So with this, I would conclude, and I'm happy to take questions.
Thank you very much, Laura, for the great talk. We have some time for questions now. Does anyone have any questions? I see some people are clapping. Right, so I don't know if there are any questions in the chat. Let me check. No. Okay. Right, so Luigi has a question. Luigi, go ahead.
Yes, thank you. Thanks, first of all, Laura, for a great presentation and a great topic. I just wanted to, you said that all these problems that you generate in the exams are different. I just wanted to ask, maybe you said during the talk and I didn't realize, it's only the formulas that are totally different or also the text? I mean, do you require the same things?
It's only the formulas.
The formulas.
So, yeah.
I mean,
So,
it's great, but I just you mentioned at some point that sometimes you ask whether something is sound or not, and sometimes you say prove that it's sound. So I thought maybe it varied a bit also in this kind of
yeah, so
sentences.
the text is generic, but I see the point. So that's actually our challenge, because of these online exams, and we had to come up with these unique exam problems, we cannot be too creative either, right? So therefore, like, for instance, if I give an abstract theory and ask two abstract theories and ask the students if the combination is finitely stable, this I cannot generate automatically. So I can only be, at least so far, we could only automate ourselves up to particular syntactic measures. And whenever some more semantics would go into, I mean, at least we couldn't come up with a solution. So we tried to make the exercises hard on them. And then, because it's still fine, it was already before hard. But the online exam is more like making sure that they master the material. But it can be, for instance, that some of the formulas, so for instance, the task is so that prove that it is sound, or is it sound, let's say like this, and some inference will be sound and some inference will not be sound. So the task would be not, so in principle it's the same task, but the result can be different. And it's actually happened that it can be different.
Awesome. Thanks.
We have another question from Luca. Luca, you can ask.
Thank you very much. Thank you, Laura, first of all, for the fantastic talk and very inspiring. My question is on the grading of the exams. So you automatically generate different exams, but if you ask me, I would really love automated grading.
Yes,
Do you have it?
me too. Let's put it this way. So that's the challenge, because you see, like, even with 45 different exam sheets, you have 45 different solutions. We did some things so we don't have automatic grading. I don't even know how to implement that, because a human proof would be as also Jeremy mentioned, that a human proof is actually very different than a computer produced proof. Can be actually very different, right? So sometimes, for instance, a computer proof whatever proof comes first, we are fine. Same with a human, but probably the human tries to go for simplicity. The computer may not, or the other way around. So we don't have a pattern for that. What we did, we tried to restrict the possible choices of for instance, for ground superposition problems, we made it so the restrictions that the proof search under the particular ordering, it's almost deterministic. So to some extent, the students there is maybe one or two choices at most, so it means two different solutions. And what we did now in Vampire for that, we extended Vampire with user-provided support. So in the sense that you can specify Vampire or the prover what ordering to be used. So to kind of really mimic the deterministic process that a student can do. But it doesn't mean that the students, what they do is always correct. So Vampire would try to make it correct, but yeah.
So the reason why I'm asking, if I can follow this up, so I've been using the Automata Tutor for a number of years, developed originally by Rajiv Alur and Loris Tantoni and many others. And now I think it's moved to the Technical University in Munich, at least the development of the tool. And what they do is they do automated grading, and they also do automated feedback. And one of this automated grading is based, as far as I recall, on computing some notion of similarity measure between the solution provided, the model solution provided by the instructor, which is stored by the tool, or it could be automatically generated in your case, and what is produced by the student. And then there is some kind of combination of 2 or 3 different measures that gives the final grade. So of course, this is a research topic, actually, is there so I'm just mentioning it here because it could lead to further research and further papers from your side. Is there any notion of similarity measure between solutions that one can devise that can be used to automate the process? But I just throw it out there.
Yeah. I think it's a fascinating question. I wish we would have an answer. I don't think I have an answer. So it's really hard to say what, definitely in terms of proofs, which are sequences of number of steps, what is the similarity there? Because every step can be different. I mean, to the invariant generation part, one similarity would be the invariance. So it really connects again to program equivalence. You know, these two programs are equivalent because they have the same invariant, but it's still too vague for correcting solutions. Yeah, but I think it's great. Yeah. Thank you as well.
Thank you. Are there any further questions? Jean-Fred?
Hi, thank you, Laura. A very, very nice talk. So if I may, I have two questions. So the first one has to do with the point on fairness in the exam generation. And I think it's not easy to define these similarity measures, I guess. So my understanding is that you use these syntactic measures, right? So essentially, syntactically, the problems have the same size. And my question is it possible to generate similar questions under this model, but in fact, they're not really similar? So one is more difficult than the other. And if it is, I mean, how could we maybe solve it?
It is. So if if you start doing it in the wild, you can get very different solutions. And as I said, the more you allow, the more probability, more solutions you get. So for instance, with our restricted model for a SAT solving problem, we generate over 2 million formulas. So we were making jokes that we will be quite happy for the next years of SAT solving, exercise in SAT solving, right? So how many students can take that? But that's exactly also posteriori, right? So you can make, so if it's completely blind, then you can come up with very simplest, so it's a random problem generation. So you might come up with a structure that uses many connectives, but pretty much uses only one logical variable or one propositional variable. Now this is something that you don't want. So you do a bit of we also do a bit of posterior filtering. But it's still not enough. So it also can be that the logical connectives that we use are too easy. I mean, they don't reflect all the difficulties in the reasoning part. So, I mean, we do, the nice thing is that for us, with only 3 variables, we came up with a large number of problems. So kind of posterior filtering was relatively easy. Well, I don't know if it's fair, but we made sure that, you know, just by the syntactic measures and the number of connectives and the program variables or the logical variables, sorry, they were fine to be similar. But you can come up with from very easy to very hard problems, or hard in a sense, you know, very, very big proofs.
Okay, so I suppose there were no students complaining then, otherwise.
Not yet, yeah.
Right. The other question I have has to do with the first problem. So generating programs from invariants. So something that was not clear to me, you said at some point that you choose pre and post conditions for which the invariant can really prove correctness of the program. But is the choice of pre and post automatic as well?
No, unfortunately not. No,
okay, so you have to do that task manually.
So that's not that great, exactly. So that's not that great as for automated deduction. So yeah, we use some templates of pre and post condition. Some are easy templates, but if you really want to come up with partial correctness proofs for inductive reasoning, it's used, and the post condition has to make use of the inductive invariant. Otherwise, true or false as an inductive invariant would also work. So yeah, so that's the fine tuning, which is still manual, and it's quite tedious.
Okay, well, thank you very much.
Thank you, sir.
We have a question from Catherine as well.
Yes, thank you, Laura, for your talk. I would like to know if you could reuse this framework to produce benchmarks for theorem provers.
Yeah, you can actually. We did it. I mean, we didn't submit anything to SAT solving community because well, for random start generation, we could actually solve, but yeah, you can generate SMT benchmarks, and we did so. So we generated quite many problems. It's unclear whether they are hard or not hard for the solvers, but we have you can use this framework, and we did it also for, especially when our recent work is on induction. So we put one additional property on the formula, and we generate inductive properties by varying the structural induction template and generate hard problems for the solvers. Sometimes these problems which we give to students can be also hard for vampire. So yeah.
Anyone have any more questions? I don't think so. So I'm curious about something. So from the first course that you have to the second, only about 10% of the students go to the second one. Do you have any insights of why that happens, or is it because of the structure of your courses, of the whole degree, not the course that you're doing?
So it's because of the curriculum, how we're organizing it, and logic and computation might not be always popular for software engineering. So they have to do formal methods. And so we have a curriculum which is called software engineering, and we have quite many great students there really working nicely with SMT based approaches, but they might not be interested, right? So they would be interested in other aspects of system or software engineering than logic and computation. And for instance, logic and computation curriculum only has 20 students, the master students. It's more a research-oriented curriculum, and for those students, automated deduction would be, it's not even mandatory, but it's highly recommended. But we get students from physics taking the course, also from the Faculty of Mathematics. So I think it's just the culture, right? So not everyone likes logic or likes debugging proofs, or even if you use the tools, they might not be interested of now, why should they do that?
Yes, of